So in a few minutes we might get a crowd of people. That will be fine.
Well, but they've been given fair warning, and no one knows that they were hoping to be on time. So since nobody's keeping an official register, it's okay if they're late. I'm glad that you've all been able to come for a colloquium today. We have on campus. Are there more like you? Eshin, are there more like you?
Yeah. On their way down?
Okay, give them a minute then.
Well, maybe I think you can begin because I'm not sure whether they're coming or not.
Oh, now you change your mind.
No, because we just had a seminar, so I'm not sure whether the students coming or not. Oh, see?
It's good to have with us this week the third, I think, in our series of department visitors. Professor Chul from University is here for several days. Just arrived yesterday, was it? Okay. Just arrived in these past few days here. Will be with us for several days more, and we're happy about that. His talk today will be on simulation methods for random vectors under specified dependent structure, and we look forward to hearing it.
Okay, thank you very much. First, I'd like to thank the department for arranging this talk and also my visit. I'm really happy to be here, and I was really impressed by this huge audience. We also operate colloquium and seminar, but there are only a few interested in it. So I'm really happy to have you everyone here. Well, I'm visiting Dr. Balkov, Dr. Chai, so very active in that. In this talk, I discuss some simulation method for generating random data. So, under specified dependent structure, here dependence means correlation between any pair of variables. My talk is in this order: first motivation and problem, and I will discuss briefly the sampling method as these are completely specified, and then I'll discuss multivariate case, multivariate binary case, which is very simple, but still there's some problem. Also, I will talk about some more general cases, and then I will conclude my talk. Here's the motivation and problem. Suppose we have data y1, y2, yk observed repeated over time from the same experimental unit. Then with these kinds of data is usually called longitudinal data. In this type of data, there are two big issues. One is there is dependence between y1, y2, and y, because these are from the same subject or experimental unit. Another problem is there is no nice way to figure out the joint distribution of these unless they are normal distribution. normally distributed variables. So then there is some problem in parameter inference. Even if we know marginal distribution of this and also correlation, still there is no way to figure out the joint density function. So there is no way to do to use the standard approach to analyze such data. In 1986, Liang and Jega suggest a nice approach, which is called generalized ring estimate equation. In their approach, they first the marginal variables so they get the marginal model. That means they introduce the class of marginal distribution. And and they try to model the mean class as a linear function of covariance, and they need a certain function here to match the range of these two parts. That kind of function G is called the link function. That is very well-known concept. They also consider correlation model alpha. So depending on the number of parameters here, they can make a lot of different types of correlation structure. So using marginal model and this correlation model, they suggest they applied kind of a quasi-likely approach to get GEE estimators. And these GEE estimators are asymptotically efficient. So they have really nice asymptotic property, but the problem is there is no way to figure out the finite sample performance. Okay? So to investigate their finite sample performance, they need simulation. Okay? Yes. It is possible only by simulation. So that is the background. So you need to generate such a type of data for these simulation studies. So the problem is here. So marginal distribution is specified. The correlation is also specified. Okay? Again, if these are non-normal, then there is no way, even if we have this information, that is not enough. There is no way to figure out joint distribution. So we are going to generate this type of data from this assumption. So we can find a lot of such data in many different areas. So that's why this simulation method is important.
So, their variance is 1. Why do you
Once you specify this, you already specify the variance. Because the marginal variance is for this marginal.
So see what is correlation?
Yeah. So if correlation is specified, then that means covariance is also specified together with this. I started with a case where density is specified. And so suppose we have a completely specified density, then how can you generate? Well, all these are really basic. So we have this density, and this is CDF, that is the inverse of CDF. We may need this definition to manipulate discrete case. Okay? But one of the simplest way is to use inverse CDF. It is well known. These specs are really well known. So if U is uniform random number, F is CDF of this random variable. If you put random variable itself into this CDF, then the resulting distribution is uniform distribution. Now, if you take inverse, then this random quantity should have distribution F. So then you only to generate the uniform random number. Right? So there are lots of algorithms for this uniform random number, so you use just that. And this is the observation from this. Right? So that is simplest way. Another approach is acceptance rejection method. So this is the density of the target distribution, and we introduce majorizing density. The definition is if any density function satisfies this for certain positive constant C, then it is called majorizing density of F. Okay? So in this approach, first we generate an observation from this one. That means we have this density, we have this density, but we are going to generate this observation from this. That really means that you might have really nice inverse CDF for G. Okay? Otherwise, there is no reason to use this, right? So, suppose we can easily generate from this density, then we may use it. So first we generate Y from this G, probably we may use this instead. And then we generate U from uniform distribution. And you compare this and this ratio, and if this is satisfied, then you accept this Y as a sample value, sample data from F. Otherwise, you just discard it, and then you go to step 1. You keep doing this. Okay? Now, it looks very strange because this Y is from G, but you are going to use this value as sample value from F. But if you understand the meaning of this, then you realize that is reasonable. Because suppose the density value at Y is very large, then you have more chance of this event, right? Because this is fixed uniform and this value is large, then the probability of this is high. If Fy is small, then the chance, this chance is small. So if you follow this, the sampling, if for the sample point that has a larger density, you have more observation from that point. So that's why this works. Okay? So that is acceptance rejection method. Now, another approach is Markov chain Monte Carlo, which is very famous in statistics. There are lots of different versions of this approach, but I'll talk about just a standard algorithm, Metropolis pacing algorithm. We start with certain conditional density. That is called the proposal density function. And also we start with initial value. You can choose any point in the support of target density. Also, the support of this conditional density should be exactly the same as this one. Now, in the first step, after in iteration t, you generate x star from this conditional distribution, and you evaluated this metropolitan ratio, which is defined in this way. And then, if this value is greater than 1, then blindly you accept x star. If not, you generate uniform random number and compare it with this ratio, and if this happens, you accept G. Otherwise, you keep the previous value. Okay? So that is the way to update. Well, the main idea is here. If this event, just think about this one. X star is here. X star is here. Okay? X star is here. So X star is here, right? So if this is large, that means this FB is large. So that makes the rate high. Right? So then this event is high. So that's why we accept it. In the other case, this density is low, so we just keep the current irreducible. But actually, this algorithm produces xt, which is Markov change. And the conditional, the proposal density, there are lots of different possible densities. You can use a lot of different ones as proposal density. Depending on that, there are many other type of algorithms. So you can even use independent chain or random chain. Still, you get the same because this is a Markov chain. So if under this condition, it converges to the unique stationary distribution, which is target distribution. So you iterate many times, and then you just pick up. Then that is going to be sample value almost from this. Okay? So I mean, regardless of this initial value, if t is large, then the sample value is almost the same as that from F. Okay? That is the main idea. Here is gift sampling. That is very similar to the previous one. But this one is for multivariate. So suppose you have specified multivariate distribution, multivariate density, and then you can use this. But in general, it's not easy to get density function for general nonlinear and joint density function. For example, multivariate gamma, multivariate Poisson, there's no nice expressions. So suppose we have a multivariate density, just assume it is like that. Then, this is the observation to generate. Now, x minus I, that is exactly the same because, but we exclude the ith component. Okay? Then this is the conditional density given this vector. Okay? So basically, this is the univariate density. Okay? Then first we start with initial value from any point in the subtotal. And in the second step, for each I, we sample, we take sample this from this conditional density. So that means you should have a nice expression for this conditional density. But if this joint density is specified, even if you don't have closed form of this one, still you can have some way you can generate this one in some way, and you're going to discuss about the details. But suppose we can generate this one from this conditional density. Then for each I, you generate this one and update this part. Okay? So whenever you generate it, you just replace the component here by new one. And if you do it for each I, then you get this. So you update it, this. You can use this one as an update. Then actually this the sequence of this is also Markov chain. That is kind of multivariate version of Markov chain, and it will converge to the distribution. Just it has the process will converge to stationary distribution, which is this. So far we discussed really basic simulation method when densities are specified. So you have complete expression for the density. In that case, you can use this method. There are many other approaches, but those are really basic. Now, let's go back to our problem. But for the time being, we focus on these binary space. So we are going to generate binary variables y1, y2, yk with this marginal probability, and there we have correlations rho ij. So pi's and rho ij's are specified. Okay? Now, as soon as you fix this pi, then there is some restriction for this correlation because from the Cauchy-Schwarz inequality, the variance is always greater than covariance. There is some inequality relation. From that, you can show this correlation is always between these bounds. Okay? So the first step is to check. You specify this value. If this one does not satisfy this, then it is meaningless to generate, right? Because there is none of observation can satisfy this. That is kind of violation. So for that problem, a lot of people did suggested their own approaches. All those are totally different. It's not like an extension. The ideas are completely different. Another thing is, they need just 30 years statistics knowledge to make these kinds of methods. Now think about it. So I really don't know how to pronounce this. Emnick, some people say Emnick, some people say Emlich. Is anyone who knows these people? Okay. Well, I'd like to read Emlich. Okay? If this name is German, then probably Emlich. Is that right? Is there anyone? Emlich. Okay. Anyway, Emlich and Siegmund's approach is good. So they can construct standard normal distribution and standard bivalent normal distribution. So everybody knows this. Right? So this is simply CTF and also bivalent CTF. Then suppose we have this standard, well, bivalent standard normal variable. If we indicate these variables in this way, so of course GPI is just quantile value of standard normal. Then if this happens, you set yi is equal to 0, otherwise 0. yi is equal to 1, otherwise 0. Then you start with the correlated normal variable, right? So this Rij is the correlation in the standard bivalent distribution. So there must be dependence between yi and yj, because you are indicating dependent variable in this way. So the binary variable should be dependent on each other. Okay? Now, if you figure out the correlation between yi and yj, you have this expression, and we are already given specified correlation. So you set these two equal. Okay? Then this part is a function of the correlation here, and you know this value, and the pi, pj's are all known. These are also known. So you are only to determine this correlation. Okay? So their approach is, their algorithm is very simple. So for each ij, you are supposed to solve this equation first, and then for each ij, if you solve this one, then you will get this value. Then you are only to put this one here, which is correlation matrix in the standard multivariate normal distribution. Then you generate this standard, these multivariate observations from this. You already have a specified value from this one. By solving this equation, you get all these values. Now, in case of multivariate normal distribution, it is easy to generate. Okay? So every software has that. So you can use that. So once you generate this one, then you just indicate. You use indicate function. So it depending on this event, y values either 0 or 1. Okay? Then all these yi will satisfy the required condition. That is their approach. Okay? Now, then what is the main problem? Well, theoretically there is no problem, but practically there is huge problem, because you are dealing. This is CDF of bivalent normal distribution, right? That means you need double integration, and bivalent normal density is also very complicated. So you are supposed to solve this nonlinear equation together with numerical integration for each I and j. There are so many pairs, so that is the real problem. Okay? But since they started with this multivariate normal correlation matrix, it can allow negative correlation. It can be any non-negative definite matrix. Okay? So that is quite general. But the main problem is computation. Okay? So now these people suggest a very simple approach, method in terms of computation. Also, the idea is very, in a certain sense, very nice. They start with independent Poisson variables. Okay? So x1, x2, x3, those are independent Poisson variables with these means. Okay? Now, they make these two variables share the common Poisson variable. Then there should be dependence, right? Because they share the common Poisson variable, so Z1, Z2 must be dependent. And this one is also, these variables are also Poisson variables. Okay? Now, if we indicate this variable, so if this value is 0, then yi is equal to 1. Okay? Then the expected value yi, which is the same as the probability that yi is equal to 1, is this one. You set this one equal to pi because we are given this information. Then you have a nice expression for this. For correlation, you have this expression. You can easily show the correlation between yi and yj. You have this expression. You set this equal to this known value. Then actually the solution is unique. You have first form of solution. So actually we have this alpha ij, which is this. If you are given correlation and marginal probability, then you can easily evaluate this. So this one, this alpha ij is the Poisson mean to be shared by Zi and Gj. Okay? Now, well, if you try to read this, then probably you will be really discouraged. But the main idea is here. For G1, G2, Gk, you are going to think about independent sequence of Poisson variables and make them share certain common Poisson variable. Okay? Because in this case, they share this x1. That's why they have correlation. Okay? Now, again, if you have many if you have Z1, Z2, Zk, then first you generate independent sequence of Poisson variables, and then you assign those Poisson variables to many of these, okay, to meet the required correlation. That is the main idea. So I'm not going to explain this, but example is much better. Very simple and much better. Always undergraduate skills ask for example rather than theory. Okay. So suppose we have this information. We have this information. No. We have PIs and correlation. So based on this expression, we have this matrix. That matrix is symmetric, so we only to consider this upper triangle. Right? Now again, from Schwarz inequality, all these diagonals should be greater than both diagonal elements. So in this case, this should be greater than this. Okay? Is that right? Greater than this. This should be greater than this and this. Right? Now, we start with the smallest positive value, in this case, you have this. Okay? Now, this value is related to x1, y1, and y2, right? So, at least the Poisson variable relating to this one should be shared by y1 and y2. But if y1 is also correlated with y3 and y2 is also correlated with y3, then y3 can share this as well, right? So we choose the smallest positive value, and we keep this one here, this beta here, and with starting with R and S is 1 and 2, those are variables related to this one. You include these two here, and then you try to make this one largest. I mean, you try to include other variable if all these variables have positive alpha values. Okay? So that means you generate Poisson variable with this mean, and that variable should be shared by all these three. Okay? So Z1 contains this Poisson, Z2, Z3 should have this Poisson variable. You do the same thing. Now, once you get this value, now you subtract, from this matrix, you subtract these times this type of matrix with element 1, 1, 1, 1. So then you get this new matrix. Okay? You subtract this value from this, you subtract this value from this, then you get this. Now, the smallest positive value is this one. Now, this the relating variable is x, y1, y3. Now, I should make this as the largest, but I cannot include y2 because this one is 0. So, well, in this case, any pair has positive alpha ij. But in this case, if you include 2, then alpha 1, 2 is 0. So you cannot include y2, but you have just this one. Then beta 2 is just this one. Now, you subtract this value from these alpha values, which are related to just this one. By doing that, you can make this matrix eventually null matrix. Okay? Now, you are only to keep the set of variables relating to this Poisson mean. You have the set of variables relating to this. Okay, you keep doing this, then eventually you will get this. Then you have Z1, well, as you see here, this is Poisson mean for the first variable, and these variables should be shared by Z1, Z2, Z3. Okay? So you have X1 is shared by this. That's the way to construct. Then you are only to indicate this variable in this. Then marginals are satisfied. At the same time, the correlation should be satisfied. Now, if you compare this method with the other one, you can do it by hand, right? You don't have to. There's no integration. There's you don't have to evaluate the probability. Okay? So you can do it by hand. So that is the simplest solution. The only problem is this works for non-negative correlation. But in many practical situations, correlation structures are non-negative because observations are from the same environment, the same subject, then there should be positive correlation. So you can apply this approach. And it covers general types of correlation structure. Now, if there is monotone property among these alpha values, that corresponds to many standard type of correlation structure. For example, MA1 structure, AR1 structure, or exchange of correlation structure. It covers all those things. Then you have this closed one. But still, we need positive correlation. So now, here is another approach by Oman and Zucker. Again, yi is binary, and correlations, they express correlations in this way. Pi ij is simply joint probability between this joint probability. Then there should be upper bound for this. So if pi is if this marginal probability is specified, then automatically you have upper bound here. Okay? So they use this notation to indicate this upper bound, and then they introduce this transformation. So ui is binary with probability. This vi is the probability that ui is equal to 1, and wi is iid from arbitrary distribution f. Then this zi, this zi is also random variable having this distribution. Okay, so then you only to indicate that. Okay. Now, if you indicate in this way, of course, this theta I is the quantile value. Then you have this relation. So now, this is the upper bound, and these are probability that y I is well, actually this ui is equal to 1. Okay. So they based on this one, you can figure out the correlation between these two should be this. Now it covers everything because we have ij here and we have ij there. Actually, they didn't use this. They used just a single constant. Okay? Well, but more generally, they are supposed to use this one. But there's a really big problem because in this case you have k combination 2 correlations, right? Because correlation is defined for 2 variables, so you have k combination 2 correlations. Now, in this case, you have V1, V2, Vk. You are supposed to find this value. Okay? From this one, you have k combination 2 equations. But your parameters are you have just k parameters. Then most case you cannot solve this, right? You have more equations than number of variables that you cannot solve. So that really means as soon as you fix this value, then it works only for that corresponding correlations. So that means this covers just only small portion of possible correlation structure. But the expression here looks like it covers everything. So you can use very limited this approach. Well, another approach is Cartesian approach, which is looks very simple and nice. His approach is based on the conditional expectation of yi given all the past observations. So lambda I is the conditional expectation, and he modeled this conditional expectation in this way. So it's a linear function of past observation. Then it turns out this variance is kind of linear combination of these variables, and you are only to solve it. So given marginal distribution and covariance, you always can solve it. That is just you are only to solve a linear equation. So starting from this binary distribution, you keep generating. So given this one, you can generate y2, where this is conditional expectation of y2 given y1. Okay? So you keep doing that. Then y should join to, well, they satisfy all the conditions. But still there is a problem, because this lambda I is a conditional expectation of binary variable. So this must be always between 0 and 1, because that is probability. Now, he tried to model this one in this form. That is a linear function. It can take even much larger value than 1, right? So sometimes this value might be outside of this interval. He also discussed some more details about this this issue, but in that case, it does not cover the given correlation structure. So there is some limitation, but it allows negative correlation. In that sense, there is a truth. Well, there are many other researches, but those that just covers just part of correlation structure or just review. Well, I prepared more, but since that's kind of already done. Thank you very much. Is there any question?
I think you can take a little bit more time.
Yeah, perhaps maybe it's another 5 minutes or so.
5 minutes.
Yeah, so
Okay.
yeah.
Okay.
Then I briefly discuss this. Now, this one is for arbitrary random. That means X is composed of these k variables, and they may have different distribution, like normal distribution and beta distribution arbitrary. No, and also, so these are specified. Also, covariance matrix is specified. So you are given VI 0. Then, how can you generate this? Well, probably most of people try to use this, but once they try to make program, then they realize it's going to be very difficult. Anyway, the Norton means normal to anything. I didn't make this very so they start with multiple standard multiple normal distribution, and if you take this transformation, then the resulting distribution is Fi. Again, this one is uniform, and you take inverse CDF, so issue. Now, you are only to determine all these correlations, right? So you have to evaluate this one. This is standard fiber normal distribution density. This is standard normal CDF, and you are also taking inverse. Usually, in many cases, this inverse is not of closed form, okay? And you need double integration. So to apply this, you have to solve this, right? So now this part is this one for each INJ. Okay? So you are supposed to solve this. That is the real headache in terms of computation. Okay? Actually, Emlich and Friedman test approach is special case of this. Basically, the ideas are the same, but the main problem is here. So now, in this case, if the component variables are infinitely divisible, then there is a much simpler approach. Well, this class of distribution contains some standard distribution, yellow distribution, like normal, Poisson, gamma, relative binomial, and so on. There are many others. If all component variables are of this type, then there is very nice approach. Actually, we can use previous approach. I mean, because Poisson variable is infinitely divisible. Okay? So we can use the same algorithm, not exactly, but similar algorithm here. So, in this approach, for the same uniform variable, you just take inverse CDF, then the correlate, this one is upper bound. Also, the covariance of this type is always increasing in delta. Actually, this will have to find something. So, we can apply also for multivariate version. Still, we have this kind. Or there must be some independent sequence of multivariate. Okay? So we are only to find alpha L and sigma. Of course, these are also pepper and matrix. So we can use the similar algorithm, but we have to find the delta in this algorithm. But look at this one. There is covariance between these two distributions with the parameter delta. Now, but you have only a single uniform random variable. So for this one, you can easily evaluate. You need just a single integration. Okay? And also, this covariance is always increasing in delta, so you can easily find the solution delta star that satisfies this, right? Because there is a unique solution. So this is monotone function of delta, then you can easily find the solution numerically with a single integration. So in terms of computation, this is much more efficient than the other. So I had example here, exactly the same form, right? So that is a related set of variable, and that is delta L, and you have to keep this one because all the components are different types. Okay? If those components are of the same type, then you really don't need this. Okay? So this one is for these things, normal, gamma, and quasicles. Then eventually we have this kind of. You only to generate uniform, IID uniform 6. In this case, you will see the 6, and you write this value in answer. Okay? Then you get the desired observation. So, well, if I conclude, no single method is expected to cover all possible correlations. My approach covers just positive correlations. Others both, but computationally too complicated. So there must be a trade-off between covering correlation and efficiency. Efficiency means computation. So when you apply, you should be very careful choosing the simulation method. Now, all these methods are totally different approach, right? For the same observation, and that is because the approach is really ideal. If you have certain insight and you have some idea, then you can easily suggest a much better approach. Okay, that's it. Is there any questions? Comment?
Are there any known hardness results? I mean, ideal for me would be something that you would want to simulate, but there is no algorithmic simulation of it. But less than that, even somewhere it's known that an algorithm would have to be really inefficient.
Well, in case of optimization, there are some standard problems, right?
Right.
So, they apply all algorithms to solve that. They already have the solution and compare. But in this case, it is difficult to figure out all possible correlation structures.
Yeah.
So we may choose a certain type of one, then there might be some algorithm which is best for that. But in generally, it might be worse. That's the situation. So it's better to make an algorithm that can cover more general correlation. Any reason?
Back on your page 5 there, your inverse CD references, you mentioned Norda. It's on page 5.
Okay. I cannot jump. Yeah.
Right there.
I usually in this way.
Yeah. Right there. I think there you can. I've seen people apply the Norda method there, where you instead you start with normal numbers and then put them in uniform numbers. Because there's a well-known relationship between the normal and the uniform.
Right.
Actually by Pearson, and so that would seem to work quite well. And it avoids a double interval.
Yeah, there are lots of, well, more generally, you may use popular. There are a huge class of popular. And I don't know whether every possible correlation can be covered by, starting with normal distribution. And it may not be covered.
No, well, because there's an upper bound. You can kind of hint at that, because you start with what we call an intermediate correlation, and it has to be greater than specified.
Yeah, right.
And so you have the, right.
Actually, Kaki's approach is, he discussed something about that. Any other?
How are you using the rest of the distribution equation?
In the Cauchy case, you are supposed to use just F inverse because you have integral form. Cauchy, you know the CDF of Cauchy, so you directly use this.
Is there a comparison study with other methods? Is there a comparison study to other methods?
Well, if we have CDF, closed form of CDF, then this one is best. Because you really don't have to repeat, right? So theoretically, that is complete. So there's no reason to use other.
Thank you. I hope many of you will be able to join us upstairs for some refreshments.
And before everybody leaves, I just want to,
Right.
I just want to say a couple of things. And first of all, I just want to say how extraordinarily pleased I am to see this whole room filled.